come to the last lecture of this meeting. A nice thing about the last lecture is that speaker can take as much time as he wants, provided audience are around. So this talk is given by Professor Sitabhra Sinha, and Professor Sinha is holding professor position both in computational biology and theoretical physics units of Institute of Mathematical Sciences. And besides, he is an adjunct faculty of the National Institute of Advanced Studies, Bangalore. He did his PhD from Indian Statistical Institute, Calcutta in 1998. His postdoctoral assignments were at Institute of Science, Bangalore, Indian Institute of Science, Bangalore, and at Weill Medical College of Cornell University, New York. Remember, he was in medical college. He joined the IMSc in 2002. His research areas are complex systems, nonlinear dynamics, theoretical and computational biology, and physics of social and economical phenomena. To be more specific, it is computational neuroscience, cardiac dynamics, ecological network, long-range correlation in DNA, system biology. He is employing modern machine learning techniques to analyze his research systems. And in math science, he is heading a large group of people. He has co-authored 2 books on pattern in excitable media and econophysics published by CRC Press and Wiley VCH. He has published many important papers in reputed journals. Today he is going to talk on maths, games and epidemics. Let us hear from him now.
Thanks, Mishraji. Alright, so the only things that we can be certain of in life, they say, are death and taxes, but I think we can add along with them diseases. So as you can see, I'm still suffering the after effects of a viral fever, and I'm pretty sure that some of you might have already undergone some of this infection which has been going around in Chennai for a while. So what has maths and in particular games got to do with it? So one of the big successes of medical science in treating diseases over the last century has been the development of vaccines for lots and lots of diseases. I mean, I remember when I was a child, the only vaccine that I probably received was the smallpox. I was probably one of the last generations who still got smallpox vaccine. You know, the doctor will give it to you and you develop this mark on your forearm and you will carry that, you know, scar for the rest of your life, so to say. Fortunately, just few years afterwards, they stopped smallpox vaccination altogether, saying that, well, smallpox has been eradicated, so no need. But when I went to get my son vaccinated a few years back, I got this huge list of all kinds of vaccines like rubella, chickenpox, measles, pneumococcal disease, mumps, and so on. Some of them are of course optional, like flu. You know, because flu you are supposed to get vaccinated every season, and many of us, you know, don't want to go through the trouble and the expense of getting a flu shot every season. But in the West, for example, getting a flu shot is pretty much de rigueur, right? If you haven't got a flu shot, you are looked upon as someone, you know, who's extremely antisocial and, you know, is somewhat almost immoral, because you are much more likely to give flu infection to all your neighbors and so on. And so if you look at it, you know, you get a large number of vaccines available, and ideally you should either get yourself or your child vaccinated with these vaccines at an early age, so that they don't run the risk of ever being infected. Now, of course, in India, you could argue that even though these vaccines exist, the lack of infrastructure makes it difficult to have many people fall under the coverage of all these vaccines. Polio has been quite rigorously enforced, polio vaccination, of course, you know, until I think about 1 or 2 years back, you know, there was this Sunday is a Polio Sunday campaign. You know, I'm pretty sure you must have heard of this, where teams from public health authorities would come to every household and make sure that if there's a child below a particular age, that child would get a polio shot. Okay? So the result of such a huge investment in resources is, that polio has almost been eradicated, except for a few pockets in, I think, Afghanistan and some parts of Pakistan. I mean, polio more or less, all of South Asia has not, we haven't had, sustained cases of polio for quite a while now. What about other diseases? Why hasn't there been a success story in eradicating other kinds of diseases? So far the only disease we have managed to successfully eradicate has been smallpox. Polio, we are almost there. There's just a few pockets are remaining. But given that all these vaccines are there, why do we still have chickenpox, for example? Why do we still have measles? Why do we have mumps? Now you might say, okay, its vaccine is still kind of not available for large number of children in villages, so maybe that's the reason why you'll have outbreaks. But isn't that surprising that in the US, for example, only this year, in June 2019, there were a huge number of measles outbreaks. Okay? Now, we are talking about a country where lack of availability of vaccine is not the issue. It's all free anyway, right? So all you have to do is, tell the public health authorities that your child needs to get vaccinated and the vaccine will be there. So how come in a situation where resource is not the issue, or lack of availability of resources is not the issue, why do we still have outbreaks of diseases for which vaccines have been available for 30 years or more? That's a big surprise, right? And what makes it more surprising was that actually measles had been declared to be extinct in the US 19 years back in 2000. So why is it making a comeback? And this is not a problem just for the US. All over the world, okay, this has been a recurring story. In fact, measles all over the world has been making a comeback. So much so that one of the senior advisors of the Center for Disease Control in the US has commented on this huge problem of vaccine hesitancy, where people, because of the very success of the vaccination program, have not seen measles cases for 2 decades, and so therefore they do not feel the need to get their child vaccinated by measles anymore. Now that's of course a kind of an ostrich mindset, because you are simply saying, okay, I've never heard of anyone getting infected by measles in my neighborhood, for donkey's years. So, do we still need to get vaccinated? And you just, don't bother. But of course, the problem is in a world where there are still pockets where measles is very much active, the chance of someone from that part of the world coming over to your part of the world and eventually spreading the disease is very much there. So until you declare, like smallpox, that it has been completely eradicated, unless the only samples of the disease exists in labs like smallpox, there is still very much a risk that there would be someone with measles coming over to your part of the country or the city and essentially causing a new outbreak. And if you're not protected, you're very much at risk of contracting the disease. So we are seeing resurgence of a large number of vaccine preventable diseases, like measles, mumps, polio, rubella, all over the world. Of course, some of these are, in less rich parts of the world, like sub-Saharan Africa, in South Asia, but also in middle-level economies like China. And what is more surprising, look at the large number of such outbreaks in Europe, Western Europe, in Australia, in North America. These are all rich countries, right? So clearly, resource availability is not the main problem. There's something else going on. How do we understand it? And if we can understand it, can we do something about it? So that's where we come in. So we are asking, can we use mathematical modeling to somehow understand what is giving rise to this vaccine hesitancy, this lack of motivation of people to get themselves vaccinated, resulting in a high risk of all these diseases which had so far been controlled, which had been effectively eliminated in parts of the world, making a comeback. And with climate change coming in, the risk of these diseases coming back in a more virulent form is bigger than ever. So clearly, we really need to understand how to make vaccines much more palatable to people, in somehow how to entice or induce people to get themselves vaccinated. So how do we apply mathematical modeling here? How do we use mathematics to understand this problem? So this problem essentially has two parts. First, we need to understand how diseases spread. How is it that someone who's infected with a disease which can pass through direct transmission? So, for example, if I sneeze, within a few meters of you, the chance of the airborne viral particles going and being ingested by you by breathing would result in you becoming sick. Or let's say by direct physical contact, where I shake your hand and then you put that infected hand in your mouth or whatever, and thereby the pathogen would get inside you and so on. So these are ways in which a disease can jump from one person to another. So we'd like to understand how this happens. How is it exactly that diseases can spread from person to person in a population? How quickly does it spread? Are there Achilles heel of this particular spreading process which we can exploit to prevent a full-scale epidemic from coming on? So that's the first part of the mathematical modeling part. The second part is trying to figure out how do people make decisions about vaccination. And we're not just talking about people making decisions about themselves. More often, because many of these vaccines are actually given to children, we are talking about how do people make decisions about whether to give a vaccine to their child or not. So how do people make decisions? Now you might say, what does maths got to do with it? This is more like the domain of psychology or sociology, right? Now it turns out that starting in the 1950s, John von Neumann, very famous mathematician, developed a branch of mathematics known as game theory, or the theory of games, which was precisely designed to understand how individuals make decisions based on information about the relative merits of their various choices. Okay. And using such game theoretic techniques, we can try to infer how is it, given certain pieces of information, people may likely to decide one way or the other to whether to vaccinate or to not. And knowing this, we can actually design inducements such that we can make people more likely to vaccinate than not. So we'll see in detail how we can model all this. So the first part is how do we model the spreading of infection. Now, in the spirit of the spherical cow, I think all of you know about this very famous story of a mathematician who was contracted by the government to find out about how to improve the milk production, and the mathematician went and met dairy farmers and to find out more about this problem. And then after months and months of meeting and interviewing various people, he produced this big report whose first line read, "Let us consider a spherical cow." Right? The idea is that mathematicians, when they approach a problem, a real life problem, they would first try to simplify it, okay, such that it's amenable to the techniques of mathematics. So in this very same spirit of a spherical cow, the simplest model of a mathematical epidemic divides an entire population into three groups of people. Okay? One group are the people who are susceptible, who don't have the disease, but who are likely to contract the disease. Okay? So they are called S for susceptible. Now, if such susceptible people come in contact with infected people, and this forms a second group of people, the I standing for infected, then with a certain probability beta, a susceptible person is likely to become infected. So we can write it in terms of a reaction. So we say that a susceptible reacting with an infected individual with a certain probability results in two infecteds. Okay, so essentially this susceptible becomes an infected person. That's what symbolically this is talking about. The infected person, in turn, after a time, would eventually either die of the disease or recover from the disease. In either case, they are removed or recovered. Okay? And so this category of population is known as R. And so the rate at which the infected go into this removed or recovered category is gamma. And so we can write this as another reaction where I goes to the category R with the rate gamma. Now, given that rate is always expressed in units of time inverse, so when you talk about rate, usually we talk about per second, per hour, per day, per month, and so on. It's not very surprising to realize that rate is just the reciprocal of a time. It is 1 over some time. So what is this time that we're talking about? It is the time for which typically you would remain infected with the disease. Okay? So all diseases have some characteristic time for which you will suffer from the disease, during which time you can pass the infection along. Okay? So let us call this average infectious period of this disease tau I. So therefore this recovery rate gamma is simply 1 over tau I. Alright? Okay, so now given this information, you can actually work out a very neat set of equations which tell you how over time the number of people in a given population would go from S state to I state to R state. So therefore you can actually figure out at any given time how many people would be susceptible, how many people will be infected, how many people will be recovered from the disease. So the first people to actually come up with this mathematical description are these mathematicians Kermack and McKendrick. So in 1927, they wrote down two coupled differential equations which very simply describe how essentially the number of susceptible, infected, and recovered individuals in a population change over the course of an epidemic. Okay? And if you just think a bit about it, this looks very trivial, right? So the first equation tells you about how the number of susceptible individuals in a population will change. So if you're familiar with differential equation, this will not surprise you that the left-hand side describes the rate of change of S. That is, over time, how does the number of susceptible individuals change? Now, how would the number of susceptibles increase or decrease? What do you think? So you have initially almost everyone in a population in susceptible category. Okay. So if you say that the total population is n individuals, initially S is simply n. Alright? Now how will this change? What do you think? What will it depend on? And the answer is there. I just want to see how you think about it. Because you have to think like, that is this intuitive? Is this natural? So what do you think? How would S change? Yes, you wanted to say something? Correct. Correct. Very good. But I want to know that what would ds dt be proportional to? So I can ask that if over a certain time, you're absolutely correct, S will decrease, but I want to know that at a unit time, the number by which S will decrease, what will it depend on? It will depend on number of infected, very good. So if there are more infected people, the chance that I will get infected is much higher if I'm susceptible, right? So obviously it has to depend on number of infected. But it will also depend on what the number of susceptible people which are already there, right? Because if there are many more susceptible people, then the number of such susceptible people who will get infected is much more than if there are only a few susceptible individuals left. So it is proportional both to the number of susceptible and to the number of infected. In fact, it's the product of these two numbers which DSDT will be proportional to. Okay, and that is precisely this, S times I. And you'd realize that there is the proportionality constant is nothing but the probability that a contact between a susceptible person and an infected person would result in the susceptible person becoming infected. Okay, and the minus sign is there because the number of susceptible person will only go down with time, because susceptible can only decrease because susceptibles will become infected and gradually get removed from the susceptible category. Okay, very good. What about the other equation? So this basically says how does the number of infected individuals change over time. Now this part is not surprising. Okay, this is simply the plus. You change this minus to a plus and it's exactly the same term. So this basically says whoever in the susceptible population lost the susceptible category adds to the infected category. So the number of infected person is getting increased by susceptible people coming into that category. So it's simply this term with a minus change into a plus. Right? What is this term? Essentially, yes. So the infected person with a rate gamma would get recovered or removed through death. Okay, and so therefore this will be proportional to I. Okay, so if you have lots of infected individuals, then of course proportionally that many more people would get recovered or removed. Okay, and that proportionality constant is simply the rate of recovery. So therefore it's very easy to see how Kermack and McKendrick wrote this equation down. Now notice, this immediately tells us what is the condition for an epidemic. So what is an epidemic? Technically speaking, an epidemic is where the number of infected individuals is growing. It's increasing with time. And so that means dIdt has to be positive. So therefore you can now turn to this equation and ask under what condition would you have dIdt positive? So that will happen when beta Si is greater than gamma I. Alright? And so therefore, if you say that I is non-zero, you can cancel I from either side and you essentially have the condition that S, the number of susceptible individuals initially, has to be greater than the ratio of the recovery rate to the probability of an infection being transmitted from an infected to a susceptible. Okay. So if you know the gamma and the beta for a particular disease in a particular population, you can work out under what condition would it result in an epidemic. Now this is very important because this will also tell us about how if you can prevent a certain section of the population from becoming infected, that is, if you give them vaccines such that they are no longer susceptible, you can actually reduce this number. If you reduce this number below this ratio, you can actually ensure that you will never have an epidemic. That is the utility of vaccination. I mean, vaccination will of course prevent the individual who has received the vaccine from getting infected, but it also has a greater social benefit. If you make enough people vaccinated such that they are no longer in the susceptible category, you can actually protect the rest of the susceptibles because now the condition for epidemic itself is not satisfied. And so when we say that a disease has been eliminated, when we say smallpox is no longer a threat, What exactly do we mean? Is it that WHO managed to vaccinate each and every person of this planet against smallpox? Not possible, right? There are many isolated populations in the world whom we have not even had contacts with, like the North Sentinelese people in Andaman Islands. Right? In the North Sentinel Island, there is a culture, there is a group of people with whom people have not been able to establish contact for centuries. So clearly, they have not received vaccines. Okay. So there will always be pockets of people whom you would not have actually given the vaccine to. But despite that, we have declared that the probability of a smallpox epidemic is essentially zero. The reason why we can say that with confidence is because of this condition. Okay. We know that given the gamma and beta for smallpox propagation in populations, the susceptible population has been reduced to much lower than the critical limit which requires an epidemic to be developed. And so therefore we can say with certainty that since we have vaccinated so many individuals, we don't need to worry. And so the aim of all vaccination programs is to somehow make sure that the number of people whom you vaccinate should be sufficiently large such that the susceptible population goes down below this quantity. Right? So that's the essence of the mathematics of vaccination. Okay? And so we essentially subsume all of this into a single number, namely the basic reproduction number, which is nothing but the product of this beta, this probability of the infection to jump from a susceptible to an infected, the reciprocal of the gamma, which is this average period of infectiousness, times the population size. So if this product of these three numbers is greater than 1, so this product of these three numbers is what is known as the basic production number, and if this product of these three numbers is greater than 1, then an epidemic is possible. If it is less than 1, an epidemic is not possible. Right? So this number is essentially the principal quantity that all epidemiologists try to calculate every time a new epidemic hits a population. Right? So when you have a new strain of influenza hitting India, for example, or let's say any of the other diseases like dengue or chikungunya, any of the transmissible diseases hit a population, the first thing that the public health authorities would try to do is to calculate this quantity. So I said that it's a product of three numbers, but there's a very intuitive way of understanding this also. It's nothing other than asking from an index case. Index case is typically the first instance of a person who comes down with a infectious disease. From an index case, on average, how many others would be infected? If this number is less than 1, that is on average, if you are infected, you will infect less than one person, it's no prizes for guessing that the chances of this disease spreading is 0. But if you can infect on average more than 1, obviously the disease is going to spread out in bigger and bigger numbers. Okay? Take the case of, like, suppose a basic production number for disease is 2. So that means on average, if I'm infected, I'm going to infect 2 other people, right? So let's say on the first day, I go down with the disease, and before I recover, I had managed to infect 2 people. Each of those 2 people would infect 2 others, and so before they recover, they have managed to infect 4. Each of those 4 in turn will infect 2, and so before they recover, they would have infected 8. So as you can see, it will start increasing as 1, 2, 4, 8, 16, 32 as a power of 2. Okay? Essentially, very soon it will result in an exponential increase in the number of infected individuals. And so, by looking at the value of this number for various diseases, we can figure out how quickly do the different diseases spread. And so people have worked out these numbers for various kinds of diseases. Like for hepatitis C, it's 2. Ebola, which was in the news last year, despite all the media attention, actually does not spread that fast. It only has an average basic respiratory number of 2. The reason, of course, people are so worried about it is because it may spread slowly, but it's a certain killer. Okay? So diseases could be deadly even if they are spreading not so fast. Right? So there are two aspects of a disease. One has to remember that. Okay? HIV is about 4. SARS, which is a kind of respiratory disease, 4. Measles is whooping 18. Okay? So if there's a measles case, if you're not already vaccinated with measles, you would have a raging epidemic in your hand, which is why you have those deadly cases of measles outbreak in US earlier this year. It is a highly infectious disease. Right? Okay. Now, the other advantage of calculating this number is from this number you can actually also work out what is the critical number of people you need to vaccinate in order to prevent a full-scale epidemic. So it's simply the fraction of population that you need to vaccinate to prevent an epidemic of a disease with a basic production number R0 is simply 1 minus 1 over R0. So this means for measles, which depending on which population you look at, you could have numbers between 12 to 18%. This means you need to vaccinate about 95% of the population. So the vaccination coverage has to be extremely good in order to prevent a measles outbreak. Okay. So even if a few families decide it's too much troublesome to get my children measles vaccine, it could actually result in measles outbreak, which is what we saw. On the other hand, influenza, which has R0 of somewhere between 1.2 to 1.8, has a vaccination coverage of 33 to 44%, which is why flu vaccines, even though they are optional, and most people actually don't get flu shots even in the US, despite that, flu is contained quite well. Okay? So this public good of vaccination, the fact that not everyone needs to get vaccinated in order for society as a whole to take advantage of the fact, is known as herd immunity. So the idea of herd immunity is that imagine that essentially you have various types of individuals, like for example the blue individuals are the ones who are not immunized, so they are susceptible, and the red individuals are the ones who have been infected. Now ordinarily, if you do not have anyone vaccinated, then essentially what will happen is a few infected individuals would cause the infection to quickly spread through the entire population so that everyone eventually gets sick. But in a situation where you got a large number of people vaccinated, so these are the yellow ones, even though you have exactly the same number of infected people, these infected people essentially cannot see the susceptible individuals. So the susceptible individuals, even though they are still likely to catch the disease if they come too close to infected person, are screened from the infected individuals by this crowd of vaccinated individuals. Right? So the screening effect of vaccination is what allows even a small portion of the population who have not been vaccinated to escape the disease. So what we do is we essentially study how diseases can spread in a social network. So, social network is a term which is not now much talked about, especially in the context of social media and so on. But it has been a concept which has been there in epidemiology from even before the advent of social media. The concept of social network is that typically when we meet with people, we are not equally likely to interact with everyone in a population. I am much more likely to spend time with my friends and family. Okay? And you are much more likely to spend time with your friends and family. And so therefore, if I'm infected, I'm much more likely to spread the infection to my friends and family rather than to some other random person in the city. And so if I have some idea about the social network of individuals, I can actually trace the course of a disease through that population. Right? So what we do is we actually study how individuals who essentially belong to these three different compartments, susceptible, infected, and removed, goes from susceptible to infected category through infection. So you can see that this individual now goes from this category to this category, and then as a process of recovery, they go from the infected to the removed category. So you can actually work out the probabilities of each of these processes. So the probability that you would be infected if you have k infected neighbors can be worked out very simply. Okay. So if you have some basic understanding of probability theory, you can argue as follows. What is the probability that if I encounter a single infected individual, I'd get the disease? I already said that's beta, right? That's the probability of the infection. What's the probability that I will not catch the infection? 1 minus beta. Okay. Now, if I have k neighbors, each of whom have the infection, what is the probability that I will not catch infection from any of them? It's 1 minus beta times 1 minus beta times 1 minus beta times 1 minus beta k inf times, because each of them is an independent process by which I can catch the infection. So the probability that I will not catch the infection from any of my infected neighbors is 1 minus beta to the power k inf. So the probability that I will catch the infection from any of them, I don't care whether I catch them from 1 or 2 or whatever, the probability that I will catch infection from any of them is simply 1 minus beta to the power k inf. Okay, and this is what is given here. The probability that an infection event will happen is simply this probability. The probability that I will recover is far simpler to calculate. It's simply gamma, or 1 over tau I. Okay. And so therefore a recovery event would happen with probability 1 by tau I. Now there's an additional thing here which we have so far not encountered, and that is a vaccination event. So the vaccination event would happen with the probability pi, and now you might ask, but how is this pi evaluated? You can of course come up with some number out of the top of your head, but that's not going to be very realistic, right? And so this is where all the other part of the mathematical modeling would focus. How do we calculate pi? Okay. So the vaccination, essentially, we need to understand this using a decision model. How do people decide whether to get themselves vaccinated or not based upon information? Okay. And for this we use the theory of games. Now the theory of games, as I said, has quite a long history. So when we talk about games, what we essentially mean are strategic interaction between agents. So that means when you and I meet and we are deciding to do something or not to do something, each of us has some aims and we have some strategies by which we wish to achieve those aims. So what are those aims? In the language of game theory, we simply say that everyone is trying to maximize their payoff. So what is a payoff? A payoff is something that is received by an agent depending upon the strategy used by that agent and its opponent. So anything that you can think of, any decision, could be framed in terms of payoffs. So for example, payoff could be monetary. So you could be, for example, playing the market. Okay, so you could have various individuals who are buying and selling equities, and the idea is how to maximize the monetary gains. Okay, but payoffs could be something else. You could be playing a game with your neighbor. You could be playing chess, and the payoff is basically win. Okay, whether you win that game or not. Okay. So a payoff essentially could be framed in terms of whatever you wish to obtain by engaging in some kind of interaction with your competitor or with your competing neighbor. And the idea is that you would try to guess what your opponent is going to do and accordingly frame your strategy such that you'll be able to win and maximize your payoff. So the way we usually formulate this games is follows. So this is a special case of games known as symmetric games. Symmetric games is where what the way that you view the situation is essentially identical to the way that your competitor is also viewing the situation. So it's where the competitors are more or less similar. This is very different from situations where you could have unequal games, like for example in games of imperfect information, where when you are trying to figure out what, let's say, a big company is going to do, you actually are engaging in some kind of asymmetric competition, because the resources you have, the information that you have, would be very different from what this big company with all its resources will have. So that's like an asymmetric competition. But let's say you are just engaging in some game with your friend. Typically, both of you would have roughly similar information, and the equal stakes in the game, so to say. And so, in such symmetric games, with two possible choices, we can write down the outcomes of the game as a 2x2 matrix. So we say that if you have two possible choices, let's call them action 1 and action 2, and your opponent also has exactly those same choices, action 1 and action 2, and I will come in a moment in an actual concrete example of what these actions might mean. Then depending upon what action you took and what action your opponent took, the two of you get different payoffs. So for example, if both of you chose action 1, both of you would get a payoff R. If both of you chose action 2, both of you would get a reward P. However, if one of you chose action 1 and the other chose action 2, the one who chose action 1 would get a payoff S and the other would get a payoff T. Now this sounds very abstract. So let me try to make this concrete by taking a particular example of such a symmetric game. And this symmetric game these kinds of symmetric games were actually mathematically solved by this person, John Nash. Anybody has seen the movie Beautiful Mind? Or have heard the movie Beautiful Mind? Okay, good. So, Beautiful Mind is about John Nash. He was a mathematician who essentially became schizophrenic, and at a very young age he had to be institutionalized. But before that, he, along with many other brilliant mathematical results, he also gave the basis for how to solve such symmetric games. So the concept that he developed, which is known by the name of a Nash solution or a Nash equilibrium, essentially uses the following criteria. So Nash equilibria is a choice of a strategy which, if you choose, then, or which if everyone chooses this particular choice, then no one would be better off by one person unilaterally deciding to deviate from that strategy. Okay? Again, it sounds very abstract, so I'll use a particular example. So one of the most famous examples of such symmetric games goes by the name of prisoner's dilemma. So usually the way prisoner's dilemma is formulated is in terms of a story, and in fact Flood and Drescher of Rand Corporation, who first proposed this game back in 1950, proposed it as a story. Okay. So what's the story? So they said, imagine the police has arrested two people, okay, Amit and Ballav, under very suspicious circumstances. So they would really like to pin a very heinous crime on them, right? But they don't really have evidence. They only know that these two characters were found loitering suspiciously in the night. Okay? So how do you make a person confess to a particular crime? So in true filmy style, they took them to separate cells and do the interrogation. So they tell each person, look Amit, if you confess, we'll let you go free immediately. But if you don't confess, and Ballav does, then you are in jail for 10 years. Okay? So what do you want? And similarly, another person goes to Ballav and says, Ballav, your friend Amit, if he confesses, he goes out immediately. But you will go to jail for 10 years. So, do you want to confess or do you want to remain mum? Okay. So, what are the choices? So, if you formulate this game in terms of this symmetric two-person game, you see the choices are cooperate, that is stay silent, or defect, which is to confess to the crime. So both of these have exactly the same choices, to remain silent or to sing like a canary. Now let's see what are the outcomes of these choices. So if both decide to remain silent, they get this payoff of R. So R is reward for cooperation. Okay. So on the other hand, if Ballav decides to sing like a canary while Amit remains silent, then Amit receives the sucker's payoff, whereas Ballav receives the temptation payoff. On the other hand, if both decide to sing like canaries, they get the P payoff, which is punishment for mutual defection. Now, very importantly, in prisoner's dilemma, the value of these payoffs have a particular order. So the highest payoff is the person who has confessed while the other person has remained silent. Okay, so let's say Amit decided to confess by Ballav remains silent. Amit immediately goes free and Ballav rots in jail for 10 years. Okay, so here T would correspond to going free immediately, while sucker's payoff, which is the worst outcome, is you rot in jail for 10 years. Now what happens if both of them decide to remain silent? So that's the reward payoff. In this particular case, the police really can't pin anything on them, but they can still put them in jail without, actually putting a case on them. So for 1 month, they are in jail. Okay. After that, the police have to let them go free. So R is 1 month in jail. And what is P? P is when both of them have confessed. Okay. So in this case, the value of each of their individual confessions is somewhat diluted because the other person has also confessed. And so let's say they still go to jail, but maybe not for the full 10 years, they go to jail for 2 years. Okay. They are given some time off because they both decided to confess. Okay. So this is immediately they go free. This is they rot in jail for 6 months. They go to jail for 2 years. They go to jail for 10 years. Okay. The actual numbers are not important. The only thing that you need to know is T is greater than R, is greater than P, greater than S. Okay, now let's have a social experiment. How many of you in this particular circumstance will decide to cooperate? No one? 1, 2, 3, 4, anyone? 5, 6. Okay, 6. How many will decide to defect? 1, 2, 3, 4, 5. Anyone? No? Okay, 6 to 5. And the rest There are no other choices. You either have to cooperate or to defect. Not making a decision is also a decision. Okay? Alright, so it's interesting because I always ask this question every time I give this talk on game theory, and the only time where the entire audience said defect is when I gave this talk to an audience of economists, which tells you something. Okay? Alright. Now, how would Nash solve this? Okay? Nash would solve this arguing as follows. He would say, okay, I don't know what the other person is going to do. Okay? So, all I'm going to make sure is that regardless of what the other person does, I will actually get the best possible outcome. Okay? So, let's first say that, okay, so let's say I am A. Okay? So, I look at B. Okay? So, I say, okay, let's first guess that B will decide to cooperate. If B decides to cooperate, which one should I do in order to get the maximum payoff? So remember, if B cooperates, then if I cooperate, I get R, but if I defect, I get T. So look at this. Which one should I do? Yes, maximum payoff is given by T, and so therefore, by this logic, if B cooperates, A should defect. Okay? Alright. But I don't know whether B is going to cooperate or not. So let's look at what's the other possibility. Other possibility is B is going to defect. So if B defects, then if A cooperates, I get a C, S. If B defects, then if A defects, I get a P. So between S and P, which is higher? P is higher than S, right? So if I want to maximize the payoff when B defects, I should defect. But it means regardless of whether B is going to cooperate or defect, I should defect, right? So Nash would say that therefore in this case you should choose defection, because regardless of what the other person does, if you choose to defect, you would get the maximum payoff. But there's a catch. The catch is the other person is not an idiot. The other person is, B is going to do exactly the same argument and would come up with the logic that I should defect also. And so therefore both will defect and thereby end up with a worse solution than if they had both been not so smart. If both were fools, they would have actually ended up better than if they were both very smart like Nash. So this is actually the other reason why it's called a dilemma. Okay, it's called dilemma because of course the prisoners don't know what to do. It's also called a dilemma because this is an outcome where individually you are trying to take the smartest decision, but you actually end up doing an even worse thing than if you had not been so smart. Okay. And this captures the essence of game theory. It tries to show the paradoxes inherent when we try to be very smart in trying to outsmart our opponent, and sometimes we can actually end up worse than before. Okay. Another such example of a game is this so-called hawk-dove or a chicken game, where the payoffs are slightly different. You still have temptation bigger than reward for cooperation, but now the sucker's payoff is actually greater than the penalty for mutual defection. So this kind of game was, for example, was studied in the context of mutually assured destruction in the Cold War. So in the Cold War, the Soviet Union and the US both had nuclear-tipped missiles pointed at each other. And the idea was that if one side manages to catch the other side unaware, then they would win big, because they would just wipe out the other country completely and decide and declare themselves winners. But the downside of that is if both decide to actually attack each other, then both wipe each other out, and that's the worst possible outcome, right? So the penalty for mutual defection is actually the worst possible outcome. So under such circumstances, Nash's solutions would say that actually the best possible strategy is a mixed strategy where with some probability you choose to play the attacker and with some probability you choose not to be so aggressive. So, depending upon what are your payoffs, you can actually come up with different kinds of strategies. And if you think that this sounds very contrived, actually we use some similar kinds of game theoretic situations in our daily life. Do we queue up or not queue up? Okay, so there's a enormously long queue in some ticket counter. Okay, you have the choice to actually be a very good citizen and stand in the queue. But then, if you're not so nice, what you will do is you'll try to scoot into the like before other person realizes, you jump to the queue, get your stuff, and say, "Ha, so long, suckers," and run out. Now the downside is if everyone that decides to do this, you'll just have a chaos in front of the ticket counter and no one will get what they want, right? And so eventually again people will say, okay, let's form a queue. But the moment you people form a queue, some person is going to be tempted to break the law. Okay? You see this every day, you try to cross the road in Chennai, right? Nobody seems to obey the traffic signals. And if you decide to be the good citizen and stand in red signal, someone's going to come and hit you, right? So, or let's say water harvesting, okay, or rainwater harvesting. Do you want to be a good citizen and decide to have this rainwater harvesting system in your house? It's no use if no one in your neighborhood does it, right? On the other hand, if everyone in the neighborhood does it, well, if I don't do it, who's going to find out, right? So you can see that all these kinds of conflict situations are very much happening in real life. And every time we take decisions, unconsciously or not, we use such strategic considerations. Okay? Now, why is this relevant to the problem of vaccination? And that's because essentially here the players are these individuals who are deciding whether to vaccinate or not, and the actions are precisely that. Do I vaccinate or don't I vaccinate? So you might say, okay, what are the costs? I mean, vaccination only has advantage. The costs are not always monetary. Yes, in a country like India, sometimes the vaccine costs a lot. But even if the vaccines are free, sometimes the cost is more like the effort involved in actually going to a place and get vaccinated. Or it could be that there could be a side effect. The side effect could be an extremely rare situation, but nevertheless, there is a finite possibility that if your child is given the vaccine, the child was going to get in a shock. Okay. In fact, there are many vaccines in which when you take the child to a hospital, the person who's administering the vaccine would say, stay here for half an hour after the vaccination, because if the child goes into a shock, we need to immediately take action. So those risks are there. They're very rare, but they do happen. So you might be tempted to say that, okay, look, this disease has never occurred in this city for the last 20 years I've been here. Why do I even take this risk, small risk that my child is going to go into vaccine shock? Everybody's child is getting vaccinated. My child is safe. Right? And so therefore, you are going to weigh the cost of vaccination against the risk of infection. And based upon this, you will take a rational decision or a strategic decision to get vaccinated or not. And so therefore, you are also in your mind unconsciously having such a payoff matrix, and based on the payoff matrix solution, you are trying to figure out whether it's more meaningful to get vaccinated or not. So what we do without getting into the complications is have each of the individuals in our model work out these matrices, work out the best possible solutions, and take the Nash solution, which is their probability that they will decide to get vaccinated or not. Now, this means that every person has to have some information based on which they decide what is this risk of infection, and on the basis of which they will decide how likely they are to get the disease. So how is this information being obtained by them? So that information could be either local, so they know how many people in their immediate neighborhood have gotten infected with the disease, It could be global. They have heard on the news that some person in Uttar Pradesh has gotten this disease. Okay. Now you might say Uttar Pradesh is very far off, but media can make a huge frenzy that people are getting infected and so on. And you might say, okay, it's really risky. Let me try to get vaccinated. Okay. So it could be global information through mass media, or it could be local information. You know from your neighbors or your friends that this disease has come to Chennai, and in fact in your immediate neighborhood. So depending upon whether it's local or global, you can actually have very different responses. So this is what we parameterize by this quantity alpha. So alpha basically says how much importance do you give to local information versus global information. So if alpha is 0, it means that you rely entirely on local information. You only care about what's happening in the neighborhood. If alpha equal to 1, it means that you're only caring about global information. You only look at what is happening in the mass media. You don't care about anything else. The other information you have is how many or what is the vaccination coverage in your neighborhood. So you know roughly how much protection is afforded by your neighbors. So now, based upon this, you can actually take decisions. And what we do is we run simulations on actual social network information. So what we have are like information about the social contact network of villages from 75 different villages in Karnataka. So we have 75 social network, and we can actually run simulated epidemics and how they take decisions about vaccinations on this social network. So on the left, you have a particular social network of a village where they're entirely relying on local information. So using local information, they are deciding whether to be vaccinated or not. The different colors, so blue corresponds to susceptible, red corresponds to people who have become infected and then recovered, and yellow corresponds to vaccinated. Exactly the same social network here also, except that now people are using global information only. Now, if you compare between the two, you would notice that you have a much higher vaccination coverage in this situation compared to this situation. So if you actually look at all these different 75 social networks, you find that typically using local information results in a higher vaccination coverage and less people eventually getting infected than if they use global information. Now you might say, okay, maybe it's, so this is the fraction of the population which eventually suffers from the disease. So as you can see, using global information results in a larger fraction of the population getting infected than if they had just had used local information. So you might say, okay, why is this? The reason this happens is it turns out that if you're using global information, you are acting in a manner of too little, too late. Okay? So what is happening is, or rather too much, too late actually. So what is happening is you are, when you're using global information, when the disease starts somewhere, it's essentially minuscule with respect to the total population. So you are not bothered. By the time the disease has completely taken over the population, it's only then that you start responding to it, but by then it's too late. The disease has already taken hold of the population and there's very little you can do. On the other hand, if you use local information, you're just responding exactly in time to whatever threat perception, whatever threat that you are facing. So it's like the Japanese Kanban, exactly the right amount in the right time. Right? So if you use local information, it results in a much more optimal response of people to this vaccination decisions than if they had used global information. So you might say, okay, maybe it's dependent on the social network. So we tried out various other mathematical models of networks. And in all of these cases, we found that actually always the local information use resulted in a better performance. So we also tried diseases with various values of this basic production number. So we tried to see how, if you look at various different kinds of diseases, how do people respond when they use different kinds of information. So if they use purely local information versus purely global information versus some mixture of local and global information, how does it function? And we found that when you use purely local information, then there is a large range of R naught in which you have coexistence of low vaccination states to high vaccination states. And this is something which is actually quite interesting in terms of how people's vaccination decisions interact with the infection spreading behavior. And so to conclude, what we're doing is we're trying to develop mathematical models to understand this vaccine hesitancy, which is one of the biggest threats threatening to offset all the advantages of that mass vaccination achieved over the 20th century in wiping out various diseases. And what we find from our models is that the source of information about disease prevalence, which people use to make decisions about threat perceptions, about whether to get vaccinated or not, depending on how likely they are to get a disease, is crucially important on the source of the information, whether it's local or whether it's global. And so what we are suggesting is that in terms of policy recommendations for public health institutions, availability or accessibility to real-time local information about disease prevalence is far more important than just having some kind of a generalized mass media campaigns. In fact, mass media campaigns, from what we find, actually may be doing more harm than good in terms of public health outcomes. All right, so with that, let me conclude. So this work was done in collaboration with my postdocs, Dr. Shakti Menon, Dr. Anupama Sharma, and Dr. Sashi Devan. And Anupama, in fact, pointed out that what I'm talking about, like why do I want to get vaccinated or not, is something that even a average 6-year-old can understand, right? And so, given that an average 6-year-old can argue like this, it becomes very important to kind of understand how is it possible to induce people to break out of this mindset and go and vaccinate themselves. All right, so thank you for your attention. I'll be happy to answer your questions.
Good evening, sir.
Yeah.
You showcase a chart wherein recently, like when you were a child, we had just the smallpox vaccine, but recently we have so many vaccines for a child to take. So my question is, rather than applying models and finding like the people who get susceptible or infected and the ones who are in need of vaccines, why can't there be models wherein we can showcase that the susceptible, that is the infected people can get recovered even through natural methods rather than vaccines? Because there are so many people, including me, who are afraid of shots, especially injections. So rather than showcasing the idea of vaccines like through injections, if it is through natural methods like for dengue usage of papaya leaves and all, so if such kinds of things are being showcased, maybe is there a possibility for people's mindset to change?
Well, obviously, if there are more painless methods of vaccination, that'd be wonderful. But unfortunately, for most of these diseases that I talked about, measles, chickenpox, and so on, there are no alternatives to vaccine shots. So, given this, despite claims to the contrary, it turns out that most of these childhood diseases, the only way to treat them is to actually give vaccines. Now, it turns out that actually having vaccination programs is not that tough, because one of the big success stories is polio, as I said. If there's a will, if there's a huge governmental effort in making sure that there would be a strong program where they ensure that every child is going to get this particular shot, they would actually make it possible. So it's not so much the pain associated with vaccine, which probably is the reason for this. Like for example, flu shots, it's there, but very few of us actually go and get it, right? Because for us, flu is not that big a danger. We know that we are very likely to catch a flu, but it's like 1 week. It's very unlikely we'll get killed. and so therefore we don't get flu shots. But of course, if it turns out that there are more convenient alternatives to vaccine, it may be people would be more likely to take them. But the point we are making is that people are always going to weigh the pros and cons of whether to go for this or not. And the idea of these models is to come up with how to induce people to do the right thing. Okay? So game theory has this concept of mechanism design. Okay? Usually mechanism design is applied to things like, for example, designing auctions. Look, for example, if you're auctioning like 5G spectrum, right? How do you make sure that all the competing companies quote the maximum possible price? Because everybody was going to try to figure out ways of quoting the lowest price. But as someone who's trying to sell it, you want to have the maximum price possible. So you would like to design the auction in such a way that people are induced to bid the highest. Okay. So in a similar manner, we are trying to come up with mechanisms by which you can actually induce people to come up and get vaccinated. Now, what you suggest could be one way. Okay. But given that so far we have not been able to come up with painless methods, painless alternatives, we are trying to come up with other mechanisms.
Sitabhra,
Yeah.
you got a chart in the game theory
Yeah.
with the 4 entry. In machine learning also there is a chart like that, false positive, false negative, true positive, true negative. Is there any isomorphism between these two?
Not that I know of.
Okay.
These matrices are like there
Yes,
everywhere.
yes.
Okay.
Uh-huh.
Here, like for example,
But
the
I think
particular
there
2 by
may be someone I can think.
yeah, the
better.
2 by 2
Yes,
matrix was
yes.
simply coming out because I
Yes,
assume there are two choices.
Yes.
If there are more than two choices, it would be n by n matrix.
Not in that sense. The concept wise, the strategy wise,
Right.
how to handle the situation. In that sense,
I see.
like there machine learning, you got recall, then you got precision, things like that. Various things you can do with that entries. Maybe something similar can be done in the game theory and vice versa. Just one open question. So if there is no question, we thank our.
Hi, sir.
Yeah.
Good evening.
Good evening.
So I see that most of the time the game theory works out with the equilibrium part in it. Like so, in first prisoner's dilemma or the other one with the Cold War, it is the equilibrium which decides or pushes people towards the point where they have to travel towards by making their best decisions, right? So shifting the equilibrium, obviously, it's not only depends on the citizen or people alone. It also depends on the government and the rules they employ and the policies they employ. So WHO also does a lot of work to monitor all those cases and report them and put them on charts. So as I could see that you are trying to make a point like okay, make use of the best. Don't go for the worst cases. Try to put up yourself into coordination cases where like you get the best choice, despite the fact of the equilibrium pushes you towards the other end. Is that right?
No, so what we are doing is we are saying that obviously people use some information to make these decisions, right? So we are looking at how the source of information actually affects their decision. And so what we find is that actually the source of information, whether they use local or global information about disease incidence, actually makes a big difference. And so as a policy decision, we are saying that it makes more sense to invest in mechanisms by which people can get actually local information in real time, rather than having some kind of a mass media based campaigns where you only get to hear about some incident which is very far away from your local neighborhood, but you might be more interested in what is happening in your local neighborhood, or you will be much more invested if the threat is actually coming from a place near you rather than which is located far away. For example, Ebola has become very well known, but it's happening somewhere in Zaire. Okay, so what are the realistic chances that Ebola can actually reach your particular neighborhood? as opposed to something which may not be so hyped up by media, but which is very much real, right? So, for example, things like, every summer or every time around this time of the year, we have incidents of dengue, right? And dengue is actually quite lethal if it happens, in a particular form, right? So, whereas, if you look at the local information about dengue is almost unavailable. Media is, for whatever reasons, media is unwilling to come up with the actual numbers of dengue cases. In fact, there are actual active efforts by certain agencies to suppress the actual number of dengue cases, which I think is very much an ostrich effect. You pretend that those cases are not there, thinking that they will go away.